My name is Zheneng Jun. Now I will start my presentation. My presentation is combine evaporative cooling technology with thermoelectric generator to improve the efficiency of waste heat recovery. So in this research, I will separate the three parts: introduction, theoretical analysis, and experimental investigation. So first, let me start the introduction part. So as you know, the extensive fossil fuel consumption by human activities has led to serious environmental problems, such like global warming, greenhouse gas emission, and climate change. And meanwhile, the use efficiency of fossil fuel also low. More than 60% of global industrial energy consumption is emitted in the form of waste heat. Unfortunately, the thermoelectric generator, which we call TG, can conveniently convert the waste heat into electricity, like in here. And the TG have a lot of advantages, such like no moving parts, compactness, environmental friendliness, and high reliability. So it will really be utilized in different areas, such like space exploration and flexible device and automobile. So the TG research fields can be divided into three parts: TG material research, and P and shape design, and heat exchange capacity improvement. So in the traditional method, the cooling water plants and the heat sink are often utilized to improve the performance of TG, like in here. So now I will start my work. First, theoretical analysis. So in my research case, I want to utilize the evaporative cooling to enhance the performance of TG. So, like in showing this figure, the cold side of the TG are covered by a thin water film. When the hot side of TG are heated, the water will be evaporation and take the heat. So it will generate the temperature difference of the two sides. So it will output the electric power by this TG. So this is the energy equation. Like shown in this figure, there's a heat transfer in some electric elements. These thermoelectric elements are composed by a p-type and n-type semiconductor, and with the electric conductor. QH is the heat input to the TG. QL is the heat disappeared from TG. And we also can write the TG output power P and TG output voltage U and TG efficiency omega. This is the TG structure and the thermal resistance network. So as we can see, figure A, in the cold side are covered by a thin water film. So it will be evaporative cooling and nature convection occurred in this water air interface. Figure B is the TG thermoelectric resistance network. By utilizing this network, we can write this kind of equations for the TG. So by determining the TG cold side heat and mass transfer, so this figure shows the cold sides are covered by a thin water film, and in the water air interface will occur the nature convection heat transfer and evaporative cooling heat transfer. So we can write these two equations. And all the parameters such like HM, rho VW, HLV are relative to the water film temperature. So in here, we have to know the water film temperature. So in here, we make a water film temperature calculation process. First, we initially guess the water film temperature T water, and by calculation process, we can know the nature convection heat transfer Q convection, and we can know the evaporative cooling heat transfer Q EVA, and we can know the TEG heat flow, QTEG. And by compare these three values, if equal to 0, it meaning that water film temperature is correct, so output. If no, calculation again until we get the correct water film temperature. And here is the result. So in here we compare the natural convection case with the evaporating cooling case. The natural convection case is the TEG cold site directly connected with the air environment. So in here, we fixed the hot site temperature at three values: 40 Celsius degree, 80 Celsius degree, and 120 Celsius degree. And in the evaporating cooling case, the environment relative humidity are changed from 25% to 75%. So by comparing the natural convection case and the evaporating cooling case, we find now the hot site temperature increase. All of the outside output voltage, output power, and output efficiency are increased. In the evaporating cooling case also, but the evaporating cooling case have much better performance to the natural convection case. And in the evaporating cooling case, by change the relative humidity, the output performance have the negligible effects. So we can know the hot site temperature can effectively affect the performance of TG. However, the relative humidity have the negligible effects to the performance of TG. And then now we will start the experiment investigation. So this is the experiment system. So this system composed by a TEG device and data recorder system and some kind of assistant system, such like a syringe pump can supply the water to the water film tank. And the PID control can control the TEG hot site temperature. And the humidifier and the chamber can control the environment relative humidity. And the TEG device can be separated to three parts: hot source, TEG, and water film evaporation pump. The hot source can be separated at the film heater, sensor, and heat distributor and insulator. And the water film evaporation pumps are composed by the fixed plates, insulated top, and the copper plates. Because the copper plate have a high thermal conductivity, so the heat disappeared from the TEG cold site can easily transfer to the water film. And before we do the experiment, we have to know. We have to get the evaporation rate for control the water film thickness. So in the case 1, we initially setting the water film at 3 mm and change the relative humidity and change the hot site temperature. We can get this kind of evaporation rate hovering. And case 2, we fix the hot site temperature and relative humidity. And we change the water film thickness, we can get this kind of evaporation rate cover and get the fitted equation. So then we will know how to fix the water film thickness. So figure A and B is for figure out the effects of the hot site temperature. First, we fix the water film thickness at 3 mm. And the environment temperature 25 Celsius degree, and the relative humidity at 15%. So now the hot site temperature increased. The whole of the cold site temperature and the temperature difference are increased. So the output voltage and the maximum output power are increased. C and B is for figure out the relative humidity effects. So we fix the house temperature and change the radiant humidity. We will find that the radiant humidity have the negligible effect to the TG performance. E and F is for figure out the water film thickness effects to the TG. So we fix the house temperature at 160 degrees and the radiant humidity at 15%. And we allow the water film thickness increase, the output voltage and the power are decreased. So it's meaning in this, the house temperature have the main effects to the TG performance, and water film thickness are also have main effects to the water output performance to the TG. But the radiant humidity have the negligible effects to the TG performance. And also we compare the evaporating cooling case with the traditional heat sink case, like shown in Figure A. The TG cold side are attached with the traditional heat sink. So this heat sink can effectively cooling the cold side of TG. And B, C, D compared the output performance of the nature convection case and the heat sink case and the evaporation cooling case. We will find the evaporative cooling case are most efficient method to enhance the performance of TG. However, in the performance research, the evaporating cooling case can effectively enhance the performance of TG. However, the water film are supplied by the syringe pump. The syringe pump needs external power, so it's not good for the detailed application. So in here, we want to utilize the capillary force to replace the syringe pump. So utilize the air-laid paper to attach the cold side of the TG, and by the capillary force, the water film can be effective power pumped to the cold side of TG. So it will so when the house heated, the water will be evaporation and take the heat. And this way don't need the external electric power. And by look out the results C, D, E, F, we find that this output performance of TG even better than the syringe pump case. So hope this result show the evaporating cooling method is an effective method to enhance the performance of TG, even compared with the traditional heat sink cooling method. And this research supported by the XMIT Corps Program of National Research Foundation of Korea, funded by the Ministry of Science, ICT. And thank you for you guys to listen to my presentation. And if you have some question, please do not hesitate to ask me. So that's all. Thank you.